So getting in the weeds with time series databases for AI. So one quick note here, I'm sure you guys noticed that I am subbing in for my coworker Anais. She's feeling under the weather, so I'll be going ahead and doing this presentation. I am also a developer advocate at Influx Data. So if you feel like connecting with me on LinkedIn, feel free. If you have any questions, let me know. Obviously within the Q&A or even afterwards, you can go ahead and find me. One of my main job duties is helping developers, work with InfluxDB and in general, just have a good experience getting it set up. So let's go ahead and get into it. So first things first, for our agenda, an introduction to InfluxDB and time series databases, projects that you can try. This will include a lot of QR codes, a lot of things that you can go ahead and investigate in your own time and just in general leverage. We find that it's very nice for people to be able to, take projects, take code that we've written and use it for their own use case. It's great, no need to write it yourself. And some tools for data processing and AI tasks with InfluxDB. So this will be going over a wide variety of tools that are available within the AI space. Because as you'll find as I go over the beginning here, we are just a time series database. So you can always imagine us as just your pure storage engine. We're not going to be your AI piece, but we integrate with a lot of AI technologies. So, introduction to InfluxDB and time series databases. So the first thing to keep in mind here is time series data is specifically data that has a timestamp. So this is data that you wish to query on that timestamp though. So you might have timestamps in your data that you're not really querying on. It's more just a timestamp that happens to be extra information, like the last time somebody logged in, for example. But that doesn't tell you, that's not really what we're looking at. What we're looking at is more about data where you have a timestamp and you want to query on it. You want to be like, in the past 5 minutes, what was the average temperature on device 22? That is a very common query that somebody would do. Or what was the, what happened 5 days ago at this exact moment in time? Can you give me a glimpse of that with this row of data? That is exactly what we look for when it comes to time series data. So time series data tends to also fall into two different categories. We tend to see sensors in the physical world and instrumentation of the virtual world. So that's going to be things like DevOps. And then in the IoT space, especially, that tends to be the real world, we could say. And the other thing to note is that there's two different time series data types. We mainly deal with metrics. Metrics are the most common data type, without a doubt. They are the regular time intervals. So you can think about something like your Fitbit, which is an IoT device in the real world that is monitoring your health at regular intervals. It's regularly checking your heart rate, your breathing, all the stuff that it gets from your body. It goes ahead and regularly stores that within a database, and then they aggregate it down for you to be able to see how well you slept last night. Events are irregular. So those tend to be something like a button click on a website, for example, is an irregular event. The button is not clicked 24/7 at regular intervals. It's clicked when somebody clicks it. So that's what we call an irregular event. They're definitely not as common. It's not that they're bad or anything. They're just not as common as a metric normally is. So time series also spans many different applications, many different use cases. I've already talked about a few of these already, but obviously we are used within various, not only industries, but also just use cases in general, because time series data is so common because, it's one of those things where it's timestamp data that you want to query on the time. It really doesn't live in one specific place or one specific use case. The other thing to note is how we differentiate from other databases. So for example, most of us here should be familiar with a relational database. We've probably used it, and it's not uncommon, obviously, for us to have them in our applications. To be clear, time series databases don't normally replace these other DBs as much as they are for a very specific use case that we just happen to be very good at. So that's more of the gist here, is that it's normally something where you have your machines running on the factory floor and they produce time series data that you store in something like InfluxDB. But then somewhere down the line, you have a SQL database that has more normal information about those machines, maybe where they were built, maybe some of their, data about when they should be maintenance or something like that, or just in general, it's other types of data that's not like a time series data. Or you have somewhere where people log into your website and they can view your time series data. That login credential information would normally be stored somewhere else. So that's just one example. And the other thing to note is that things like Mongo can also store time series data, same with Elastic, but they don't tend to be quite as good about being Like Elastic, for example, is very good at search time series data, not so much for more open-ended, you could say. And Mongo, although it can store all kinds of time series data, isn't always indexing on your timestamp, so sometimes query performance can be affected because of that. So we tend to see things as one time series data, timestamp data is one of the big things that differentiates it. You have that timestamp, that's the primary index in particular. That means that primarily our files are indexed on time. We deal with a high write thoroughfare. So we deal with a lot of people who are dealing with thousands of sensors, and a sensor will normally send you a data point roughly every second or even nanosecond or millisecond. And so we're dealing with a ton of data coming in all at once. And so that's a big thing that people need, is they need the database to be able to ingest all of this data efficiently. The ability to obviously query over time ranges efficiently, which again comes down to that primary index. And we also offer aggregations within our version of SQL. So you can do things like averages, sums, and also offering different granularities for your time ranges, things like minutes, hours, and days. And of course, scalability and performance. Specifically, we are designed to scale horizontally to handle things like increased load and just in general be often across distributed clusters of machines. So for reference, InfluxDB is built on top of the Apache Arrow Data Fusion project. So, sorry, those are two different projects, but it's built with those two. And then all of our file systems are in Parquet, which is good because sometimes our customers require that they can go ahead and download all their Parquet files. And obviously we use SQL as our query language, which is important because a lot of outside tooling expects SQL. It expects to be able to query your database in SQL, which means that if you don't have a SQL DB, you don't have a SQL language compiler, you're going to run into issues where just certain things are just not going to really work. You're going to have some kind of middleware that basically translates the data that you pull from one database and inserts it into another. So being able to take advantage of that is really important to us. So we're going to go over some ML projects you can try. Now, first thing I do want to highlight, though, is I do want to highlight the flights. So this is Flight SQL, Flight Arrow. And basically what this allows you to do is within Python, it allows you to take advantage of our Flight client library. And so specifically here, we have our InfluxDB client library for Python, which is being imported at the top, pretty straightforward. Then we have our installation for it. So with that, you have your host, which is your URL. This can be either a local host or something cloud-based like this one is. You have your organization ID. That basically is just a part of the authentication. Then you have your token. Your token is what says what is allowed to be read or written into your database. And then you have your actual database name underneath. So those four components basically help authenticate and make sure that you have permission to either write or read from your database. Then you have the client, and basically the client just takes all those together and goes ahead and instantiates the client. So that way then you can go ahead and start querying or start sending data in as well. In this one though, we're just showing a query as an example. So with this one, we're saying select all from our table, where we go ahead and query. We're selecting the language as SQL and the mode as pandas. So that way then we receive our data back in a pandas data frame. This is all really important for the upcoming demos, etc., because this is pretty much how we integrate with a lot of our outside technologies, is through things like our Python client library. This is one of the example projects. It provides an example of how to use Quix and InfluxDB to build a machine anomaly detection data pipeline. It contains the full data pipeline as a project, but does not include the data simulator. But in the getting started, it will explain how you create that data simulator. But this is one example that takes advantage of the flight that I just talked about. So basically how this works is that there are many areas where you can look for and monitor problems in the industrial IoT space, whether it's from the physical space, the actual mechanics of those machines, but sometimes it's from the technology, whether that's the control system or the operators. But ideally, we automate the solutions to the monitoring of these spaces to reduce our errors and downtime. So let's imagine the following scenario. We have a packing company that's having issues. We don't know the root cause, but we're getting a lot of errors. We don't know why a machine is failing and don't know how to identify what's causing it. When it's running normally, the data exhibits strong cyclical and seasonal patterns. It's a very predictable pattern, in other words. However, when it starts to break down, it also exhibits a different known pattern. The question becomes, how can we use something like, for example, HiveMQ, MQTT, and InfluxDB to automate and identify this pattern and anomaly? So the goal of the demo is that I'm going to describe today is to highlight how we can perform this type of work for this use case and hopefully give you the confidence to try it for yourself. So you can see how easy it is to be adopted by someone, for example, on the floor. So this one is taking advantage of, just to be clear, it's taking advantage of HiveMQ, MQTT, and Hugging Face as well. So let's go into this next one. Here's a complete data pipeline architecture. So throughout this demo, we will refer back to this to understand the stages of data movement and in general, just the transformation of this data. So given our hypothetical problem, this would be our solution architecture, which again is just the data journey. We have, for example, 3 robot arms that are packing robots. These robots are synced to our HiveMQ broker, which then uses the Quix MQTT client to ingest the data in real time and feed it to our Quix destination InfluxDB plugin, which basically will then just send it onward. Then we're going to write that data to a table called machine_data with all of our raw and historical data in InfluxDB. From there, we'll use the quick source InfluxDB plugin to query the data back out into Quix. We'll run it through an ML model, pass the results back to InfluxDB in a new table called ML results. Then we'll use Grafana to visualize the data, our ML results, and alert on these anomalies. We'll also be talking about Hugging Face in a second too. So yeah, we're taking advantage of a few different tech here to be clear, but basically HiveMQ is working as our MQTT broker, which connects to our MQTT client, which within Quix is our data processing engine. So I just noticed now that the Quix logo is missing. That data processing engine is pretty much all being done via Quix. So from Quix, it goes ahead and it sends the data to our original machine data table, which can also obviously hold some of our old historical data, which we can use for that anomaly detection. So imagine this architecture obviously going on for more than just a day. It's not just because we're receiving errors. We also have the historical data to pull from as well. But then it's going ahead and it's pulling that data back out and throwing it into an ML model, which then leads to an ML results table. So basically we query it back out of Influx, including that historical data. We throw it through the ML model, which we'll get to in a second. Then we send it back up to a destination called ML results. And all of this will feed back into Grafana in the end. And with Grafana, we can not only look at the original machine data, but we can also look at the ML results as well. And with Grafana, we can take advantage of some of their alerting as well. So in an ideal world, if one of our robots was failing, we would see our vibrations spike like this, where we would have a constant incline which plateaus. We can use a basic threshold to alert our team to this issue. So it would be easy to say this is how simple our problem was. However, this is not very real world, to say the least. In the real world, our data behavior isn't always that easy to derive. What we can do in this instance, where most of our data points fall into a particular range, but as you can see, we need to rely on a pattern or spread of our vibration readings to understand if an issue is occurring. Basically, we are seeing a different type of seasonality here. In this case, now we take advantage of an artificial neural network to help solve our problem. In this case, we have chosen an AutoEncoder. It is unsupervised, essentially where it tries to learn patterns without labels or prompts from me. It was actually originally used for image compression, but we can now use it for time series anomaly detection. How the mode works is for the input, it's like telling the robot that it will learn a dance made of specific basic steps. So let's say we put it like input_dim would be different steps. Then we have our sequence layer. The sequence layer is not a standard layer, but if we were to imagine what it might do, it prepares the sequence of dance steps to be learned over a certain number of beats or time steps. Then we have our LSTM layer. They're like the robot's memory. As the robot watches the dance, it uses these layers to remember the actual sequence. The first layer with 16 units could be seen as the robot focusing on remember the main parts of the dance. Then the second layer with only 4 units is it trying to remember the key movements that define the dance style. Then you have your encoding layer. The dance moves are encoded in a simpler form. Imagine the robot now has a compressed memory of the dance focusing on the most important moves, which is the output of the second LSTM layer. Then we have a repeat vector. This is like the robot getting ready to recreate the dance. It takes the core memory of the dance and prepares to expand it back into the full sequence. From there, we have decoding these LSTM layers. It's just the robot trying to recall the full dance from its core memories. It starts with the essential moves and then builds up the detail until it has a full sequence. And then finally, a time-distributed dense layer. This is like the robot refining each move. It ensures that each step in the dance is sharp and matches the original as closely as possible, ready for the robot to perform the dance itself. Or in our case, the robot would be able to, for example, judge you and how you dance. Very similar, actually, if you think about how some dancing games like Dance Dance Revolution kind of watch you on cameras, and then they match up your own dance movements. It's a very similar for this, dumbed down explanation. That's basically what we're describing here, is how that game would work. But obviously, when used with things like historical data from these robots, it would be able to discern faster and easier than we can exactly what is expected behavior and what is not expected behavior, because it has all of these layers to look at and interpret the data that it has. So the next one that we're going to be going over is from time series to vectors. So this is a blog post by my coworker that discusses integrating time series data with specifically vector databases. So we did a presentation for ODSC webinar about, I want to say 2 months ago, back in May, where we discussed basically some of the differences between vector DBs and time series databases. But basically the big step here is what I've already talked about. InfluxDB is a time series database good for monitoring and holding IoT data, etc. But a vector database, for this example, we used Milvus, excels in managing high-dimensional vector data. And obviously, it can do things like performing advanced similarity searches, essential for your AI insights. The post itself details a workflow where the data from InfluxDB is queried, normalized, and converted into vectors, and then stored in Milvus for performing those similarity searches. We're going to be demonstrating this using an example where we have traffic data, including conditions like accidents or unusual traffic that can then be used to identify anomalies and understand our overall traffic patterns. It also explains the requirements and steps to set up our environment. For example, we use things like Docker, Jupyter Notebooks, an InfluxDB cloud instance. Additionally, it covers the concepts of vector databases and their importance within the AI and machine learning landscapes and how they handle the challenge of high-dimensional spaces throughout advanced indexing techniques. The tutorial then concludes with a practical example of generating some dummy traffic data, processing it, and using both InfluxDB and Milvus for a real-world application scenario. So this is a wonderful, this is much more easy to understand now that I can just, contextualize it in this architecture diagram. So as you can see here, both of these databases are basically receiving the data for all intents and purposes. They're receiving it slightly differently, and the fact that InfluxDB feeds back into Milvus, and combined together, they can actually show these kind of patterns. So to better understand the relationship between these two, obviously, it's helpful to contextualize their use within this example. So imagine you're trying to develop a platform that offers real-time traffic monitoring and pattern recognition to improve a city's traffic management. Specifically, you want to create a solution that identifies when the traffic conditions are operating anomalously and determine the type of traffic anomaly present, like whether that be like an accident, traffic, construction. And by traffic, I mean like normal traffic. InfluxDB would store the time series data from those sensors, while Zillow would store the image data and manage the search indices for complex queries. So in this scenario, you could continuously monitor your traffic data, like, for example, average speed and vehicle count in InfluxDB, while you might also be collecting traffic images in Milvus. When traffic conditions fall outside the norm, you can send this data to Milvus, then you can perform a similarity search in Milvus to identify this type of anomaly. Milvus was, and when I say Milvus also, this is just in general most vector databases. I'm just using the name because it's easy. It is primarily designed for handling high-dimensional vector data, not raw video files, for example. However, you could still use it to work with video data by first converting it into like a form that Milvus can handle, specifically vector embeddings. There are other databases out there that are better for handling video data. I just wanted to make note of that. So with this, you would do like feature extraction. This would be when you extract features from the video using, for example, like deep learning models or other algorithms that can represent those video frames and segments. These features could be based on the appearance, motion patterns, and other relevant characteristics of the video content. From there, these are converted into the vectors that the vector database stores. It can represent a frame or a segment or key characteristics. Then you go ahead and just do the storage. And then when it comes to search and retrieval, it's performing similarity searches to retrieve the videos or video segments that are most similar to a query vector. This can be useful in applications, obviously, such as things like video recommendation, surveillance, which is kind of what we're doing here, or content-based video retrieval. So basically, although it can't store like a raw video file, it can go ahead and basically take screenshots of the videos and contextualize what it's seeing within them. So it could see things like many people are walking around, or there's lots of cars where there are not normally this many cars sitting around because there's a high level of traffic, for example. But it would vectorize those characteristics out. Something like many people would be a vector for all intents and purposes, or maybe there's a lot of like red cars for some reason. It would probably be able to differentiate and be like lots of red cars. I guess it's like a red car meetup here at this traffic light. So one thing that is crucial though for this is normalizing our time series data with pre-processing for data analysis, especially when we're working with time series data from different sources and scales or preparing data for those machine learning models. Normalization brings different time series data sets to one common scale without distorting the differences in the ranges of value or we're trying not to like lose any information as well. Essentially, it enables you to retain and compare the shapes of your time series data in a similarity search without bounding the comparison to a range, for example. There are several types of normalization methods, things like min-max normalization, z-score normalization, decimal scaling, and more. In this example, we are using z-score normalization, which involves rescaling the data so it has a mean of 0 and a standard deviation of 1. The goals here are uniformity, to bring it all to a common scale, making it just in general easier and easier to compare and combine this time series data from these different sources, which will obviously have different different units. This is especially useful when you want to include multiple correlated time series in your vector. For example, if you're monitoring weather patterns, you might want to take a multi-dimensional vector with humidity and temperature time series data. And this also helps with improved model performance as well. So normalized data will often lead to a better performance in machine learning models or accuracy and similarity searches by ensuring that the scale of data does not bias the learning process. And also just in general compatibility. Vectorized and normalized data is compatible with a range of analytical tools and algorithms, which is just going to be way more straightforward when you actually want to do your analysis. So basically, after we normalize our time series data, we can then vectorize it. Vectorization, if you don't know, is basically just a process that involves transforming this time series into a format suitable for machine learning and also suitable to be within a vector database. It's just basically vectorizing the data so it can be stored within a vector DB. It involves things like feature extraction, segmentation and windowing, encoding, reshaping, and padding. In this tutorial that I already discussed, just to clarify, the QR code is the first thing, then we go into how this actually works. So the one I already showed, windowing involves this is how you would basically run this. So the next demo, this one is actually going to be something that you can go ahead and look at yourself, but basically this is within an industrial IoT environment. This is a CSTR machine, which basically, from what I understand, circulates water within a cooling, basically it's circulating water within like a cooling container. This is good for when you're making things like pharmaceuticals, occasionally things like food and stuff. You need to be able to keep stuff within a certain temperature range. And basically that's what this machine is doing. It just, it pays attention to things like the temperature within different ranges within the device. And then it circulates that liquids, or it doesn't even always have to be a liquid. Sometimes it actually has solids inside of it from what I understand. And basically it just circulates them to go ahead and make sure they're all within the appropriate range, if that makes sense. Like I said, this is a very specific industrial IoT case, which is why we're not going to go into it, but we do put the QR code here for your, so you can go take a look at it if you would like. So the next thing we're going to do is some use cases with ML and InfluxDB. So these are a few of our customers, and I'm just going to go over how each one of them is using things like ML with Influx. So one thing to note is obviously they all store their data in Influx, and then some of them we can talk about what they're using. Some of them we can't quite talk about the, exactly what they're doing. But basically to start with, Izako. Izako is a startup specializing in machine learning, artificial intelligence, and in general time series analysis. It created what they call a Apolgo, a time series augmented analytics platform. It uses AI to automatically detect anomaly in a streaming in streaming time series data. They predominantly have customers within the aerospace, automotive, and telecom sectors. Their clients' data is mostly sensor and telemetric data. They use InfluxDB to power Apolgo, their time series management platform. After considering many different types of databases, they picked InfluxDB because we were the easiest to work with some of their outside analytics tooling, and they wanted to really be able to focus on providing their clients with the best machine learning and not having to deal with like storage, etc. The next one is Gotion, which is a leading vehicle electric battery and battery management system manufacturer. They are they're headquartered within Silicon Valley, but the company's goal is to just in general create the next generation of battery tech. Their R&D centers are all over the world, and in general, they are working on creating, for example, a solution for vehicles, including the first mass e-commercial bus route. So e-bus route, sorry. So basically, they're working on creating batteries that can go within e-buses, which is just an electric bus, that would allow them to go further distance and be able to service more people. They're also currently working on a new data platform for EV and energy storage batteries with analytics and machine learning features. They found that InfluxDB is very good at data compression, which is helping them save on their long-term storage costs for the company because they need to store so much historical data in particular to be able to run and feed their machine learning. So that's the other thing to keep in note, is that when you're working with machine learning data, you do normally need to, store quite a bit of historical data so we can learn off of that, which means you have to think a little bit less about just your real-time monitoring and more about your overall storage cost for the long term as well. They also like the fact that we had a SQL query language, which allowed things like aggregations and selectors, which just in general reduce their, overhead of having to learn something brand new. Strive, formerly Switch, creates a one-of-a-kind cardholder experience that inspires loyalty. This is straight from their website, by the way. The company's secure, proprietary, and patent-pending automation will give cardholders the ability to manage and update all of their online accounts in one place. So things like form filing, login, and updating account info. It wants to build a platform that helps users get their cards into use immediately or update their online payment profiles. And the task of moving this is very complex. So to build their credit card updater, Switch realized that they needed an anonymized site navigation for machine learning to enable their remote process automation. And that's pretty much all I can say about this one because it's still under development, so that one can't be talked about too much more. The next one is Veritas. When it comes to the need to automate storage forecasting and their SaaS platform, they were able to provide predictive insights. They're using AI and machine learning to deliver a predictive support service for their appliance customers. Previously, they measured their problems through their auto support capabilities. They had years of this auto support information and hundreds of millions of telemetry data points from more than 10,000 appliances, but they didn't have any analytics for forecasting to enable preventing problems from happening. Visibility, you could say, was a rear view mirror. The availability of this vast amount of time series data collected for use internally from their auto support enabled them to forecast for a multitude of use cases from application performance to workload anomaly detection. Yet the challenge was to automate a historically manual process handcrafted for the analysis of a single data series of just tens of data points to large-scale processing of thousands of time series and millions of data points. In the end, they chose Influx to tackle these issues because of the amount of scale they were dealing with, and again, the amount of historical data that they needed to store and be able to retrieve, obviously. So we're now used for their storage for their forecasting implementation, and this allows them to help basically take care of the forecast when the appliances are going to need things like updates, changes, repairs in general, things within the real world that need fixing, you could say. And then the final one would just be Capital One. So Capital One is, most people probably are aware, they're a very large bank here within the US. So for them, their time series data consists of things like infrastructure, application, and business process metrics. The combination of these metrics are what they rely on for observability, which allows them to basically just help serve their customers. They're also building a solution to basically monitor their internal, I'm trying to think of the words here. Yeah, basically their internal server infrastructure is what they're using us for. So that one's a pretty straightforward one. And I'm going to leave it at that because I don't want to run out of time on this. So I'm going to continue onward because this is a very long, this is very wordy. I did not realize how wordy this was until I was going through it. All right, so overview of task in InfluxDB 3.0. So one thing to note is InfluxDB 3.0 favors interoperability with other ETL and stream processing tools instead of locking users into InfluxDB specific task tooling. So users have access to a wider variety of streaming and task tools so they can find the one that works best for them. Having more choices requires, though, greater initial decision making, you could say. So some tools for task would be something like Mage AI, for example. Mage AI is an open source alternative to Apache Airflow. It's an open source ETL tool, and it has a UI that simplifies overall the ETL process. Some of the advantages of Mage is obviously that it's open source, which is great. We always love open source. It's easy to use. Some of the features it has is orchestration for scheduling and managing data pipelines. It has a notebook editor, which is interactive with Python, SQL, and R for coding those data pipelines. It has data integration, so it syncs data from many third-party sources to your internal destinations. It allows for things like streaming, and it has DBT, which would build, run, and manage your DBT models with Mage. It also has clear documentation on how to deploy on AWS, Azure, DigitalOcean, GCP, and with Terraform and Helm charts included, which is very great for a lot of people. Here are some of the resources for that we have created for Mage with InfluxDB 3.0. So with this one, I would just suggest grabbing a screenshot, and then you can literally just, obviously these are all hyperlinked, but unfortunately I didn't get the chance to put QR codes into this. But basically what I would do is I would just look up, these are all blog titles, that's how you can find these again. But for example, we have a blog that highlights how to set up a simple downsampling task, which I haven't defined yet, but downsampling is when you take your historical data and you aggregate it down. So something like for data that's more than 2 days old, go ahead and downsample it down to the average per hour. So normally when you're dealing with IoT devices, you end up with data points roughly every second or so. And so that can be quite large to store long term. And so it's very practical to downsample and create it, aggregate it down basically. So that's one example. The next one is using it for anomaly detection with InfluxDB and Halfspace Trees. And then ETL Made Easy. With that one, it's just an on-demand, webinar where you can do best practices for using Mage as an ETL tool and InfluxDB. And I think it also extrapolates a little bit further on the anomaly detection one as well. And then you just have the actual documentation and demo. The demo itself uses the Python client along with Halfspace Trees to identify anomalous behavior in machine data in particular. So for those of you guys who don't know, Halfspace Trees is basically data is partitioned with a hyperplane in the feature space. Hyperplanes are randomly generated. Additional planes are added to recursive split the data set and partition it until the number of points in a partition reach basically a minimum threshold. Each additional plane creates a node in that tree. Anomalies are defined by the point's depth in the tree or whether they exist in the smaller partitions. I would definitely suggest trying this one out yourself, and this one does come with a QR code, so it's nice and easy to take advantage of and try. So we'll go on ahead. Another thing that you can take advantage of is AWS Fargate. Now, obviously, this is specific to the AWS ecosystem, but basically it's a serverless compute engine for containers that works with both Amazon Elastic Container Services and Amazon Elastic Kubernetes. Some advantages to Fargate are serverless simplicity. It abstracts away the underlying infrastructure, allowing developers to deploy containers without worrying about provisioning, scaling, or managing EC2 instances. And it has pretty good cost efficiency because they are charged on the resources consumed by the containers, which can then be a lot of cost savings by limiting the need to maintain idle EC2 instances. When it comes to Fargate and InfluxDB, we have another example of a downsampler, and then a blog post that compares the costs associated with using Fargate to continuously run a container that had built-in scheduling and some monitoring for downsampling tasks with InfluxDB, and using CloudWatch to schedule the runs. This was more of an expensive option for this use case where the runs were periodic and on a consistent data load. So basically, instead of running this continuously, it can be run on a task or on a cron job, for another way of saying it. This is the downsampling example. So again, I'm going to leave that up for 1 second. All right, and then the next one will be function as a service tools. So FAS tools are event-driven serverless computing platforms. Examples will be things like AWS Lambda, Google Cloud Functions, and Azure Functions, for example. So some advantages and considerations: it lets you run your code without provisioning or managing your servers. It automatically scales up, obviously. If your execution time is long, for example, longer than 10 minutes, a serverless compute solution like Fargate might be more cost effective, though, one thing to note. If your task is intermittent or has a variable load, you won't pay for the idle compute resources with an FAS. If the workload is consistent, Fargate might be the more cost-effective option. And these solutions allow users to focus on developing complex analytics and data science logic, so there is less granular control over the computing environment. Bytewax is a framework designed for building data processing pipelines with a focus on streaming and stateful computations. It is particularly suited for tasks that involve real-time data processing, such as ETL pipelines, event-driven architectures, and continuous analytics. So this is another good one. Unfortunately, we don't have an example of using it, but some advantages to Bytewax are things like stateful computations, where they provide support for allowing you basically to manage your state across multiple data events effectively. They have parallel and distributed execution, so you can scale across multiple cores and machines. They have a Python integration, which is really important, especially for us and those familiar with the Python ecosystem. Window and time-based operations, which allows you to do advanced windowing capabilities such as tumbling, sliding, and session windows, which are normally quite essential for time-based aggregation and analytics. They also have many different connections and integrations into various data sources and sinks, including databases, message queues, and file systems. And they have an event-driven architecture. The next one would be Apache Kafka, which is an open source distributed event streaming platform capable of handling trillions of events a day. And then the other one would be FAST, which is a Python stream processing library built on top of Kafka. It provides stream processing features similar to Kafka streams, but it's designed to be used within Python applications. So it allows you to build distributed, fault-tolerant, and scalable applications with ease. So they each have unique features and advantages that make them suitable for ETL tasks. So for example, when it comes to Kafka, it has high throughput and low latency. So it can handle a high volume of messages with low latency, making it suitable for especially real-time data processing. It's extremely scalable. It scales horizontally, so you can add more brokers to your Kafka cluster to handle any increase in load. It's known for its durability and reliability. It provides a strong durability by persisting messages on disk and replicating them across basically multiple brokers, which also makes it very fault tolerant as well because it's replicating the data. It can also do things like pub/sub messaging, where it supports both publish, subscribe, and queuing models. It also has integrations with a wide ecosystem. So it integrates very well with things like Apache Spark, Flink, and Kafka Streams. And with that, it has obviously the support for stream processing through Kafka Streams, which is basically a client library for building applications and microservices, enabling you to process real-time data directly within Kafka. So Kafka, especially when it comes to ETL, can be used for things like data ingestion, where it's the first place where the data is ingested, and then it can send things to databases and other sinks. Good for data transformation, especially because you can transform your data on the fly before you load it into your downstream systems. Data integration, because again, it's already got all those integrations to go with, and real-time analytics. So FAS, though, has other advantages. So obviously it's providing a user-friendly API for Python developers, which makes it very easy to build on top of. It already has the stream processing built in, similar again to Kafka Streams. It's pretty easy to use. It's got a pretty intuitive API, so that's reducing a lot of complexity. So obviously the docs are pretty decent. You don't have to fight too much with it. By integrating with Kafka, it's basically taking advantage of pretty much all the Kafka advantages I just mentioned. It also has an actor model, which is good for building concurrent and distributed applications. And it also has fault tolerance as well because it's inheriting them from Kafka. And its use cases are pretty much the exact same as well. So some examples also of using these two together would be something like you first ingest your data with Kafka brokers, then you data process them with FAS, and then you data output them either back to Kafka topics or to other things like databases, data links, or real-time dashboards, for example. And these are some more resources here at the end of this slide deck. So you can sign up for free for InfluxDB Cloud. We don't ask for a credit card or anything like that. You can go ahead and learn more from our blogs, our documentation. InfluxDB University is our free learning resource. And then we also have our community. Our community is where you can also ask us questions. We have both community forums and Slack where we help our community members get up and going.